A solid fuel rocket or solid rocket is a rocket with a rocket engine that uses solid propellants. The earliest rockets were solid fuel rockets powered by gunpowder. They were used in warfare by the Chinese, Indians, Mongols and Arabs, as early as the 13th century. All rockets used some form of solid or powdered propellant up until the 20th century, when liquid propellant rockets offered more efficient and controllable alternatives. Solid rockets are still used today in model rockets and on larger applications for their simplicity and reliability. Since solid fuel rockets can remain in storage for long periods, and then reliably launch on short notice, they have been frequently used in military applications such as missiles. The lower performance of solid propellants does not favor their use as primary propulsion in modern medium to large launch vehicles customarily used to orbit commercial satellites and launch major space probes. Solids are, however, frequently used as strap-on boosters to increase payload capacity or as spin-stabilized add-on upper stages when higher than normal velocities are required. Solid rockets are used as light launch vehicles for low Earth orbit payloads under 2 tons or escape payloads up to 500 kilograms. Basic concepts. A simple solid rocket motor consists of a casing, nozzle, grain, and igniter. The grain behaves like a solid mass, burning in a predictable fashion and producing exhaust gases. The nozzle dimensions are calculated to maintain a design chamber pressure, while producing thrust from the exhaust gases. Once ignited, a simple solid rocket motor cannot be shut off, because it contains all the ingredients necessary for combustion within the chamber in which they are burned. More advanced solid rocket motors can not only be throttled but also be extinguished and then reignited by controlling the nozzle geometry or through the use of vent ports. Also, pulsed rocket motors that burn in segments and that can be ignited upon command are available. Modern designs may also include a steerable nozzle for guidance, avionics, recovery hardware, self-destruct mechanisms, APUs, controllable tactical motors, controllable divert and attitude control motors, and thermal management materials. Design begins with the total impulse required, which determines the fuel oxidizer mass. Grain geometry and chemistry are then chosen to satisfy the required motor characteristics. The following are chosen or solved simultaneously. The results are exact dimensions for grain, nozzle, and case geometries. The grain burns at a predictable rate, given its surface area and chamber pressure. The chamber pressure is determined by the nozzle orifice diameter and grain burn rate. Allowable chamber pressure is a function of casing design. The length of burn time is determined by the grain web thickness. The grain may or may not be bonded to the casing. Case-bonded motors are more difficult to design, since the deformation of the case and the grain under flight must be compatible. Common modes of failure in solid rocket motors include fracture of the grain, failure of case bonding, and air pockets in the grain. All of these produce an instantaneous increase in burn surface area and a corresponding increase in exhaust gas and pressure, which may rupture the casing. Another failure mode is casing seal failure. Seals are required in casings that have to be opened to load the grain. Once a seal fails, hot gas will erode the escape path and result in failure. This was the cause of the Space Shuttle Challenger disaster. Grain geometry. Solid rocket fuel deflagrates from the surface of exposed propellant in the combustion chamber. In this fashion, the geometry of the propellant inside the rocket motor plays an important role in the overall motor performance. As the surface of the propellant burns, the shape evolves, most often changing the propellant surface area exposed to the combustion gases. The mass flow rate, and, therefore, pressure of combustion gas is generated as a function of the instantaneous surface area and linear burn rate. Several geometric configurations are often used depending on the application and desired thrust curve. Circular bore, if and Bates configuration, produces progressive-regressive thrust curve. End burner, propellant burns from one axial end to other producing steady long burn, though has thermal difficulties, center of gravity shift. C-slot, propellant with large wedge cut out of side, producing fairly long regressive thrust, though has thermal difficulties and asymmetric CG characteristics. Moon burner, off-center circular bore produces progressive-regressive long burn, though has slight asymmetric CG characteristics. Nozzle, usually a 5 or 6-legged star-like shape that can produce very level thrust, with a bit quicker burn than circular bore due to increased surface area. Casing, the casing may be constructed from a range of materials. Cardboard is used for small black powder model motors, whereas aluminum is used for larger composite fuel hobby motors. Steel is used for the Space Shuttle boosters. Filament wound graphite epoxy casings are used for high-performance motors. The casing must be designed to withstand the pressure and resulting stresses of the rocket motor, possibly at elevated temperature. For design, the casing is considered a pressure vessel. To protect the casing from corrosive hot gases, a sacrificial thermal liner on the inside of the casing is often implemented, which ablates to prolong the life of the motor casing. Nozzle. A convergent-divergent design accelerates the exhaust gas out of the nozzle to produce thrust. The nozzle must be constructed from a material that can withstand the heat of the combustion gas flow. Often, heat-resistant carbon-based materials are used, such as amorphous graphite or carbon-carbon. Some designs include directional control of the exhaust. This can be accomplished by gimbling the nozzle, as in the Space Shuttle SRBs, by the use of jet vanes in the exhaust similar to those used in the V-2 rocket, or by liquid injection thrust vectoring. An early Minuteman first stage used a single motor with 4 gimbaled nozzles to provide pitch, yaw, and roll control. LITV consists of injecting a liquid into the exhaust stream after the nozzle throat. The liquid then vaporizes, and in most cases chemically reacts, adding mass flow to one side of the exhaust stream and thus providing a control moment. For example, the Titan IIIC solid boosters injected nitrogen tetroxide for LITV. The tanks can be seen on the sides of the rocket between the main center stage and the boosters. Performance. A typical, well-designed ammonium perchlorate composite propellant first-stage motor may have a vacuum-specific impulse as high as 285.6 seconds. This compares to 339.3 s for kerosene liquid oxygen and 452.3 s for hydrogen-oxygen bipropellant engines. Upper-stage specific impulses are somewhat greater, as much as 303.8 s for APCP, 359 s for kerosene-oxygen and 465.5 s for hydrogen-oxygen. Propellant fractions are usually somewhat higher for solid propellant first stages than for upper stages. The 53,000 kg Castor 121st stage has a propellant mass fraction of 92.23%, while the 14,000 kg Castor 30 upper stage recently developed for Orbital Sciences Taurus 2 COTS launch vehicle has a 91.3% propellant fraction with 2.9% graphite epoxy motor casing, 2.4% nozzle, igniter and thrust vector actuator, and 3.4% non-motor hardware including such things as payload mount, interstage adapter, cable raceway, instrumentation, etc. Castor 120 and Castor 30 are 2.36 and 2.34 meters in diameter, respectively, and serve as stages on the Athena IC and IIC commercial launch vehicles. A 4-stage Athena 2 using Castor 120s as both first and second stages became the first commercially developed launch vehicle to launch a lunar probe in 1998. Solid rockets can provide high thrust for relatively low cost. For this reason, solids have been used as initial stages in rockets, while reserving high specific impulse engines, especially less massive hydrogen-fueled engines for higher stages. In addition, solid rockets have a long history as the final boost stage for satellites due to their simplicity, reliability, compactness and reasonably high mass fraction. A spin-stabilized solid rocket motor is sometimes added when extra velocity is required, such as for a mission to a comet or the outer solar system, because a spinner does not require a guidance system. Thicol's extensive family of mostly titanium-cased star space motors has been widely used, especially on Delta launch vehicles and as spin-stabilized upper stages to launch satellites from the cargo bay of the Space Shuttle. Star motors have propellant fractions as high as 94.6%, but add-on structures and equipment reduce the operating mass fraction by 2% or more. Higher performing solid rocket propellants are used in large strategic missiles. HMX, C4H8N4, NO2, 4, a nitron with greater energy than ammonium perchlorate, was used in the propellant of the Peacekeeper ICBM and is the main ingredient in any PE-75 propellant used in the Trident II D5 fleet ballistic missile. It is because of explosive hazard that the higher energy military solid propellants containing HMX are not used in commercial launch vehicles except when the LV is an adapted ballistic missile already containing HMX propellant. The Naval Air Weapons Station at China Lake, CA developed a new compound, C6H6N6, NO2, 6, called simply Cl20. Compared to HMX, Cl20 has 14% more energy per mass, 20% more energy per volume, and a higher oxygen-to-fuel ratio. One of the motivations for development of these very high energy density military solid propellants is to achieve mid-course exo-atmospheric ABM capability from missiles small enough to fit in existing ship-based below-deck vertical launch tubes and air-mobile truck-mounted launch tubes. Cl20 propellant compliant with Congress 2004 insensitive munitions law has been demonstrated and may, as its cost comes down, be suitable for use in commercial launch vehicles, with a very significant increase in performance compared with the currently favored APCP solid propellants. With a specific impulse of 309s already demonstrated by Peacekeeper's second stage using HMX propellant, the higher energy of Cl20 propellant can be expected to increase specific impulse to around 320s in similar ICBM or launch vehicle upper stage applications, without the explosive hazard of HMX. An attractive attribute for military use is the ability for solid rocket propellant to remain loaded in the rocket for long durations and then reliably launched at a moment's notice. Propellant families Black powder propellants Black powder is composed of charcoal, potassium nitrate, and sulfur. It is one of the oldest pyrotechnic compositions with application to rocketry. In modern times, black powder finds use in low-power model rockets, as it is cheap and fairly easy to produce. The fuel grain is typically a mixture of pressed fine powder, with a burn rate that is highly dependent upon exact composition and operating conditions. The performance or specific impulse of black powder is low, around 80 seconds. The grain is sensitive to fracture and, therefore, catastrophic failure. Black powder does not typically find use in motors above 40 newtons. Zinc sulfur propellants composed of powdered zinc metal and powdered sulfur, ZS or micrograin is another pressed propellant that does not find any practical application outside specialized amateur rocketry circles due to its poor performance and incredibly fast linear burn rates on the order of 2 meters per second. ZS is most often employed as a novelty propellant as the rocket accelerates extremely quickly, leaving a spectacular large orange fireball behind it. Candy propellants In general, candy propellants are an oxidizer and a sugar fuel that are cast into shape by gently melting the propellant constituents together and pouring or packing the amorphous colloid into a mold. Candy propellants generate a low-medium specific impulse of roughly 130s and, thus, are used primarily by amateur and experimental rocketeers. Double base propellants DB propellants are composed of two monopropellant fuel components where one typically acts as a high-energy monopropellant and the other acts as a lower-energy stabilizing monopropellant. In typical circumstances, nitroglycerin is dissolved in a nitrocellulose gel and solidified with additives. DB propellants are implemented in applications where minimal smoke is required yet medium-high performance is required. The addition of metal fuels can increase the performance, though metal oxide nucleation in the exhaust can turn the smoke opaque. Composite propellants A powdered oxidizer and powdered metal fuel are intimately mixed and immobilized with a rubbery binder. Composite propellants are often either ammonium nitrate-based or ammonium perchlorate-based. Ammonium nitrate composite propellant often uses magnesium and/or aluminum as fuel and delivers medium performance, whereas ammonium perchlorate composite propellant often uses aluminum fuel and delivers high performance. Aluminum is used as fuel because it has a reasonable specific energy density, a high volumetric energy density, and is difficult to ignite accidentally. Composite propellants are cast, and retain their shape after the rubber binder, such as hydroxyl-terminated polybutadiene, cross-links with the aid of a curative additive. Because of its high performance, moderate ease of manufacturing, and moderate cost, APCP finds widespread use in space rockets, military rockets, hobby and amateur rockets, whereas cheaper and less efficient ANCP finds use in amateur rocketry and gas generators. Ammonium dinitramide, NH4N, NO2, 2, is being considered as a 1-to-1 chlorine-free substitute for ammonium perchlorate in composite propellants. Unlike ammonium nitrate, ADN can be substituted for AP without a loss in motor performance. Polyurethane-bound aluminum APCP solid fuel was used in the submarine-launched Polaris missiles. APCP used in the Space Shuttle solid rocket boosters consisted of ammonium perchlorate, aluminium, iron oxide, polybutadiene acrylonitrile, PBAN, polymer, and an epoxy curing agent. It developed a specific impulse of 242 seconds at sea level or 268 seconds in a vacuum. The 2005 to 2009 Constellation program was to use a similar PBAN-bound APCP. In 2009, a group succeeded in creating a propellant of water and nano-aluminum. High-energy composite propellants typical HEC propellants start with a standard composite propellant mixture and add a high-energy explosive to the mix. This extra component usually is in the form of small crystals of RDX or HMX, both of which have higher energy than ammonium perchlorate. Despite a modest increase in specific impulse, implementation is limited due to the increased hazards of the high explosive additives. Composite modified double base propellants Composite modified double base propellants start with a nitrocellulose nitroglycerin double base propellant as a binder and add solids normally used in composite propellants. The ammonium perchlorate makes up the oxygen deficit introduced by using nitrocellulose, improving the overall specific impulse. The aluminum also improves specific impulse as well as combustion stability. High-performing propellants such as NEPE75 used in Trident 2D5, replace most of the AP with HMX, further increasing specific impulse. The mixing of composite and double-base propellant ingredients has become so common as to blur the functional definition of double-base propellants. Minimum signature propellants One of the most active areas of solid propellant research is the development of high-energy, minimum signature propellant using C6H6N6, NO2, 6 centiliters-20 nitrone, which is 14% higher energy per mass and 20% higher energy density than HMX. The new propellant has been successfully developed and tested in tactical rocket motors. The propellant is non-polluting, acid-free, solid particulates-free, and lead-free. It is also smokeless and has only a faint shock diamond pattern that is visible in the otherwise transparent exhaust. Without the bright flame and dense smoke trail produced by the burning of aluminized propellants, these smokeless propellants all but eliminate the risk of giving away the positions from which the missiles are fired. The new CL-20 propellant is shock insensitive as opposed to current HMX smokeless propellants which are highly detonable. CL-20 is considered a major breakthrough in solid rocket propellant technology but has yet to see widespread use because costs remain high. Electric solid propellants Electric solid propellants are a family of high-performance plasticell solid propellants that have the unique property of being ignited and throttled by the application of electric current. Unlike conventional rocket motor propellants that are difficult to control and extinguish, ESPs can be ignited reliably at precise intervals and durations. Moreover, the technology is attractive because it requires no moving parts and the propellant is insensitive to flames or electrical sparks. Hobby and amateur rocketry, solid propellant rocket motors can be bought for use in model rocketry. They are normally small cylinders of black powder fuel with an integral nozzle and sometimes a small charge that is set off when the propellant is exhausted after a time delay. This charge can be used to trigger a camera, or deploy a parachute. Without this charge and delay, the motor may ignite a second stage. In mid and high power rocketry, commercially made APCP motors are widely used. They can be designed as either single-use or reloadables. These motors are available in impulse ranges from D to O, from several manufacturers. They are manufactured in standardized diameters, and varying lengths depending on required impulse. Standard motor diameters are 13, 18, 24, 29, 38, 54, 75, 98 and 150 mm. Different propellant formulations are available to produce different thrust profiles, as well as special effects such as colored flames, smoke trails, or large quantities of sparks. Designing solid rocket motors is particularly interesting to amateur rocketry enthusiasts. The design of a successful solid fuel motor requires application of continuum mechanics, combustion chemistry, materials science, fluid dynamics, heat transfer, geometry, and machining. The vast majority of amateur-built rocket motors utilize a composite propellant, most commonly APCP and candy rocket propellant. History: solid rockets were invented by the Chinese. The earliest versions were recorded in the 13th century. Hyder Ali, king of Mysore, developed war rockets with an important change: the use of metal cylinders to contain the combustion powder. Castable composite solid rocket motors were invented by John Whiteside Jack Parsons at Caltech in 1942 when he replaced double-base propellant with roofing asphalt and potassium perchlorate. This made possible slow-burning rocket motors of adequate size and with sufficient shelf life for jet-assisted takeoff applications. Charles Bartley, employed at JPL, substituted curable synthetic rubber for the gooey asphalt, creating a flexible but geometrically stable load-bearing propellant grain that bonded securely to the motor casing. This made possible much larger solid rocket motors. Atlantic Research Corporation significantly boosted composite propellant ISP in 1954 by increasing the amount of powdered aluminum in the propellant to as much as 20%. The largest solid rocket motors ever built were Aerojet's 3 6.60-meter monolithic solid motors cast in Florida. Motors 260 SL1 and SL2 were 6.63 meters in diameter, 24.59 meters long, weighed 842,900 kilograms and had a maximum thrust of 16 mn. Burn duration was 2 minutes. The nozzle throat was large enough to walk through standing up. The motor was capable of serving as a 1-to-1 replacement for the 8-engine Saturn I liquid propellant first stage but was never used as such. Motor 260 SL3 was of similar length and weight but had a maximum thrust of 24 mn thrust and a shorter duration. Use Sounding rockets almost all sounding rockets use solid motors. Astra B, Black Brant, S310, S520, Terrier Orion, Terrier Malamute, VSB-30. Missiles due to reliability, ease of storage and handling, solid rockets are used on a number of missiles and ICBMs. Air-to-air missiles, AIM-9 Sidewinder, ballistic missiles, Jericho, ICBMs, LGM-30 Minuteman, LGM-118 Peacekeeper, RT-2PM Topol, DF-41, Agni V. Orbital rockets solid rockets are suitable for launching small payloads to orbital velocities, especially if 3 or more stages are used. Many of these are based on repurposed ICBMs. Scout, Athena, Mu, Pegasus, Taurus, Minotaur, Start-1, PSLV, alternating solid and liquid stages, Shavit, Vega. Larger liquid-fueled orbital rockets often use solid rocket boosters to gain enough initial thrust to launch the fully fueled rocket. Delta II, Titan IV, Space Shuttle, Ariane 5, Atlas II, Atlas V Delta IV, HIIA, HIIB, PSLV, optional solid boosters to lift heavier payloads, GSLV Mk3, solid fuel is also used for some upper stages, particularly the Star-37 and the Star-48, both manufactured originally by THECOL, and today by Orbital ATK. They are used to lift large payloads to intended orbits, or smaller payloads to interplanetary or even interstellar trajectories. Another solid fuel upper stage, used by the Space Shuttle in the Titan IV, was the Boeing-manufactured Inertial upper stage. Pioneer 10 and Pioneer 11 were both sent out of the Solar System by Star-37E upper stages from Atlas Centaur rockets. Voyager 1 and Voyager 2 were both sent out of the Solar System by Star-37E upper stages from Titan IIIE rockets. Magellan was sent to Venus on an IUS after being deployed from Space Shuttle Atlantis on STS-30. Galileo was sent to Jupiter on an IUS after being deployed from Space Shuttle Atlantis on STS-34. Ulysses was sent to Jupiter on an IUS and a Star-48 PAM after being deployed from Space Shuttle Discovery on STS-41. It then was placed in a polar orbit around the Sun following a gravity assist around Jupiter. New Horizons was sent out of the Solar System on a Star-48 PAM from an Atlas V rocket. Some rockets, like the Antares, have mandatory solid fuel upper stages. The Antares rocket uses the Aerojet rocket manufactured Castor 30 as an upper stage. Advanced research, environmentally sensitive fuel formulations such as Alice propellant, ramjets with solid fuel, variable thrust designs based on variable nozzle geometry, hybrid rockets that use solid fuel and throttleable liquid or gaseous oxidizer. See also, fireworks, pyrotechnic composition, ammonium perchlorate composite propellant, intercontinental ballistic missile, GTEx engine, Space Shuttle solid rocket booster, Crawford burner, skyrocket. References. External links, Robert A. Brajernik rocket propulsion page, Astronautics composite solid propellants, Ariane 5 SRB, Amateur High Power Rocketry Association, NACA Rocketry, 5 Cent Sugar Rocket, Practical Rocketry, NASA Practical Rocketry.